Hello everyone. Let's begin with a fascinating group of compounds that you've definitely encountered in daily life: aldehydes and ketones. From the vanilla in your ice cream to the nail polish remover on your shelf, these compounds are everywhere. Both aldehydes and ketones contain the same functional group, the carbonyl group, written as C double bond O. But what makes them different is how this carbonyl group is attached. In aldehydes, it is terminal, represented as a CHO. In ketones, it is placed in the middle of the chain, written as a COR prime. Because oxygen is more electronegative than carbon, the C double bond O is strongly polar, which influences all their chemical properties. The position of this carbonyl group is what defines whether we call the compound an aldehyde or a ketone. In older literature and in laboratory usage, aldehydes and ketones are often referred to by their common names rather than systematic names. For aldehydes, the common names are usually derived from carboxylic acids. You simply replace the ending "ic acid" with the word aldehyde. For example, CH3CHO is called acetaldehyde, which comes from acetic acid. A benzene ring with ACHO group attached is called benzaldehyde. Ketones, on the other hand, are often named by mentioning the two alkyl groups linked to the carbonyl carbon, followed by the word ketone. For instance, CH3COCH3 is commonly called dimethyl ketone or acetone. These traditional names are still widely used in everyday chemistry practice. Now let's turn to the systematic IUPAC system. For aldehydes, the rule is simple: take the longest carbon chain that contains the CHO group and give it the suffix -al. For instance, CH3CH to CHO is called propanol. Remember, the carbon of the CHO group always gets position number 1, so there is no need to mention its location explicitly. If substituents are present, we number the chain accordingly and add them as prefixes. For example, CH3CH to CH to CHO is butanol. This method ensures consistency in naming, especially when the molecules become more complex. For ketones, IUPAC naming uses the suffix -1. You pick the longest chain containing the carbonyl group, number the carbons to give the carbonyl carbon the lowest possible position, and then write the name. For example, CH3COCH3 becomes propanone, which you know as acetone. In another case, CH3COCH to CH3 is named butan to -1 because the carbonyl group is at the second carbon. Notice that in ketones, we must indicate the position of the carbonyl group with a number, except in propanone where its location is obvious. This numbering avoids ambiguity when the carbonyl group could appear at different positions along the chain. In addition to numbering, aldehydes often use Greek letters to describe the carbon atoms relative to the carbonyl group. The carbon directly attached to the CHO group is called the alpha carbon. The next one is beta, followed by gamma and delta, and so on. Substituents are described accordingly. For example, in the compound CH3CH with bromine on the second carbon, then CH to CHO, we call this beta-bromobutyraldehyde. This convention is extremely handy when talking about reactivity patterns because reactions often involve the alpha or beta carbons. Finally, let's consider aromatic aldehydes. When a benzene ring carries ACHO group, the compound is simply called benzaldehyde with the formula C6H5CHO. For substituted derivatives, the carbonyl group is given position 1 and other groups are named relative to it as ortho, meta, or para positions. For instance, you can have orthonitrobenzaldehyde, metanitrobenzaldehyde, or paranitrobenzaldehyde depending on where the nitro group sits on the ring. Aromatic aldehydes like vanillin, which gives vanilla its characteristic flavor, retain their traditional names even in IUPAC nomenclature. This shows how historical usage and systematic rules often blend together in organic chemistry. So, to sum up, aldehydes and ketones are all about the placement of the carbonyl group. Common names often come from carboxylic acids or alkyl substituents, while IUPAC names use the systematic suffixes -al for aldehydes and -1 for ketones. Greek letter notation gives us a quick way to locate substituents, and aromatic aldehydes frequently retain their traditional names like benzaldehyde and vanillin. These naming conventions are not just rules, they are the language of chemistry, allowing scientists across the world to understand each other without confusion. I hope this helped you see how systematic and fascinating organic nomenclature really is. In the next class, we'll dive deeper into their structures and reactions, where the real fun begins.